I'll push the start button. Okay, so this is analyzing baseball data with our lucky chapter 30. I think we got 2 more chapters to go. So I'll share my notes here if I can find it. Is this it? Yeah. Hopefully you can see now the notes for chapter 13. If you don't, yell loudly. So this is the objective of this chapter was to look at home run hitting, in particular, some of the factors that determine home runs for balls already in play, not necessarily whether they got hit or not, but if you got a ball in play, um, then what are the factors that determine whether that was actually a home run or just a single or some other um, play, some other result like that. So this chapter looks at the dependence of home runs primarily on this launch angle and exit velocity thing. That is how high the ball was hit and how fast, right? So the idea is that certainly a faster hit ball should be more likely to be a home run. But you'd imagine that some very high launch angles end up being, of course, pop flies. It's always you're yelling from your seat. Oh, yeah, no, it lands right where the guy's standing with the glove ready to pick that ball right out of the air, right? And a little bit of look at the spray angle, how that depends, like hit it to the left field, to the right field, and then park effects. That's a revisit park effects. We already looked at park effects, but now we're going to look at just from the perspective of the home run data. And at the end, there's a quick look at comparing the 2021, 2023 home runs. So that's basically that. So getting the data, the book just pulls in this data file called SC balls. I guess it's StatCast balls in play 2020, 2023. This file is not in the repo that they provide. And it just says follow the guidance in chapter 21, but chapter 21 doesn't produce this file either. So and then we can make you do some work right away, make you understand things. So you're gonna go back to chapter 12, chapter 21. No, I meant chapter 12. There's no chapter 21, chapter 12. And but it's not that bad. You just have to pull down the 2 seasons of StatCast data following the same templates that they provided, filter down the balls in play, which I did do, so you can do that. And then I basically had to look at chapter 13 and see which columns I needed because it was different columns than what they used in chapter 12. So just do that. And then you can combine it. You can combine the 2 years together and save it as an RDS file, or even better, as Parquet file, because that turns out to be 10 times smaller. So this is the code. I won't go through, but this is basically cut and paste, or I shouldn't say cut and paste, but kind of cribbed from chapter 12, putting together the code from that chapter, combining things together, grabbing the columns that he uses in this chapter, and then I actually created also the season home run in that database for whatever reason, but actually I got to fix it because I took that code out, so I'll take that out of that select statement. I can remember to do that. And then I saved it not as a RDS, but rather as a Parquet file because the RDS was like 40 megabytes. That's a little bit on the big side for GitHub. But Parquet is 5 gigabytes, 40 megabytes. The Parquet is 4 megabytes, so that's plenty small enough to include in the repo. So that was kind of nice. So that's a little benefit of what we learned from the previous chapters from Rich Ricardo there. So appreciate that. Let me make a note to fix that. Select this case. Anybody ever wants to run that code. Okay. So that's the code. Now we're back to the book chapter. We read in the 2 seasons, generate the a column that's just the same. Just I don't know why he did this. There's already a column called I guess no, he wanted the year. That's right. So he takes the year from the game date and turns it into a season variable. It's just the year. And then if the event's a home run, we want to have a little indicator variable, home run for 1. The 0 is not a home run. And so then for the first part of this work, we're just going to focus on 2023. And so this is what the data looks like. There's that indicator variable and the season variable that I mentioned. So this is just a key. There is a primary key for the game itself. We don't use that. There's the date. There's the batter ID. There's a pitcher ID. We will use those in a moment. The event, where the batter was left-handed, right-hander. The pitcher was right-handed, left-handed. The total hit distance, This HCX, HCY is where the ball landed, I guess. But I couldn't figure out what the coordinates for this were. It says something, it has you in the appendix, and it's not really crystal clear. Probably the StatCast documentation tells you. He does some manipulations of this, which I just accepted them and try to understand. If anybody wants to, when we get to that point, anybody wants to jump in and give their opinion on exactly the coordinates, it's clearly in the same distance, same units as the hit distance, but other than that, it's not clear what the alignment of it is. On the baselines, is it? I don't know. I assume it must be on the baselines, but then I don't understand the transformation. Then there is the launch speed and angle. We mentioned that before. That's interesting. I just noticed that's supposed to be right in the dirt, right in the picture, right in the knees. Um, the home team, the away team, and then we already mentioned the season. So that's the data. And again, like I said, we made a parquet file. That's awesome. Makes it much smaller. Oh, here you go. Ricardo said. Okay.
Yeah, the units is in feet.
Okay, yeah. No, but the orientation, so it's like perpendicular to the catcher then?
Yeah, from the perspective of the
Okay,
catcher.
I gotcha.
Yeah. Yep.
Okay. All right, cool. That makes
That's
sense.
that's the starting point. Poop.
Yeah. Okay. Awesome. So the first thing the book does is take a look at um, the home run probability. So we've got data, it's a one or a zero, so this if it's a home run or not. So we're going to use a logistic regression, but using a generalized additive model just to smooth it out. You can use something else here, Gaussian process, whatever you want, but just to smooth out so that we can get a feel for the probabilities of the home run as a function of launch angle and launch speed. So this is how you call that. You need this library. I don't know what it stands for, but I think it does mixed model. I think the M stands for mixed models. I think it does mixed models with general additive models. But here we're just using a simple smoother for launch angle, launch speed. And that's pretty straightforward. With all our models, there's a predict function. You can just tell, hey, give us some new data, and it'll give you what the prediction is for that. And that's exactly what we need to like make a nice little smooth plot. And so that's what he does. Here's the code for what it's worth. You just make a little grid, do predictions for all the points in the grid, and then use ggplot for GM contour. It's straightforward. So the point of this is to look at this as a function of look at the probability of hits, home runs, sorry, as a function of launch speed and launch angle. And we can see, as we thought, yeah, sure, better launch speed, you're more likely to get a home run. And also, as you probably would expect, well, launch angle, for small launch angles, you're probably not going to get a home run, ground out. And then for high launch angles, you're more likely, you might get a pop fly. So somewhere in the middle is kind of this sweet spot of getting the distance to get out of there, get out of the park, right? And so we should look at that. So that's the next thing is just bin that up. Let's just look only at, not bin it, but just look only at the fast, hard hit balls, and then plot a smooth of that. Here we're just going to use Geom Smooth, though we're not going to use GAM. Geom Smooth can do it for you as well. I think no, maybe not. I was going to say maybe you could do that. Maybe you didn't even need to use MGCV, but I'm not sure. Anyway, I mean, it can't do 2D. It does it'll do it for you, right? Inside Geom Smooth. Does it do 2D? Could we have done I just want anyone know, could we have done this other plot with just ggplot, letting it do its own smoothing? Something to think about, I guess. But anyway, here we're just going to use ggplot's built-in ability to do these kind of smooths, and here we can see, yeah, there's an optimal launch angle somewhere just under 30 degrees to get the maximum chance for home run. That's fine. The next thing takes a little departure into, I forgot to mention this, but temperature effects. So conventional wisdom is that warmer temperatures lead to more home runs, so we can check that. There's temperature data that's already included. So this data, this temp 2023 is included in the Analyzing Baseball data with our package. So is this parks. So we only care about outdoor parks, or because the indoor parks, the temperature is controlled. So the outdoor temperature won't matter. Right? So we focus on outdoor parks. That's all this does. And I don't know, it looks like there is some trend for on warmer days, you get slightly more home runs. So it seems to hold up. I guess that's the point of that, right? The next section in our hodgepodge of home runs is to look at uh, the spray angle. So here's this calculation I was talking about. So he calculates the location X, location Y, and so this makes it sound like it's not quite the HC and X, the X and Y is not quite orthogonal to the 0, 0 might be at the catcher point, but I'm not sure how it's oriented, the X and Y, because this looks like he's doing a rotation here. And some kind of offset. So I don't know. Oh no, it's not a rotation. So it's just anyway, the appendix talks about this, and I apologize, I didn't have time to delve into what the heck is exactly going on with this. This part seems clear. Like you've got location X, location Y, calculate the angle. But this coordinate transformation, I don't know what's going on there. These magic numbers always bother me. It's like, why do you have magic numbers in there? In any event, I trust him. He's an expert at this. This is the spray angle. We can then look for home runs from the StatCast 2023 events for balls in play, and we can then say, hey, what was the distribution? And also we'll show the hit distance, but what was the distribution of spray angle and hit distance for home runs? So that looks like, that seems to make sense. This is looks like every outside stadium area. There's some interesting outliers. He points out, I don't know what happened there, but that somehow became a home run. Did
That
you
was
mention what that was?
that was an inside the park home run.
Yeah, it's quite inside, but yeah. One in the pool at the Arizona Diamondbacks Chase Field. Actually, the pool's on the other side, but anyway. So the only thing he does with this data is take a look at whether or not hitters tend to hit, left-handed hitters and right-handed hitters tend to hit against a certain side or not. And it does seem to be the case that if you use a facet wrap to split this up from left-handed to right-handed pitchers, they do tend to hit home runs in the pull direction, as they call it. That is toward the side of the field that they're standing on. And that seems to hold up quite a bit. In fact, the left-handers seem to pull even more. It's a little bit further pull for them than it is for the right-handers. Then there is ballpark effects. Oh yeah, C7, right? I didn't. Like I said, I didn't really read that in detail, but go back and look at it. I will after this myself, but I encourage you to do that as well.
Yeah, that's where, he goes into detail about that formula, where those numbers are coming from.
Okay. Yeah, I'll take a look at that too. I meant to, and things got away from me. So in this one, we're just looking at home and away home runs for each team, and then calculate this park factor here as a ratio of home runs to away home runs. It's pretty straightforward. Nothing new here, really. We kind of did this before, but we can then, do a little plot of this. And yeah, sure, there's some like standouts like Texas and Cincinnati, and yeah. Wait, that's supposed to be, I thought you said New York Yankees. Where's the, maybe I wrote the wrong thing. I think that's Cincinnati. But anyway, the blue line represents neutral. And that's it. I mean, I don't know. What do you want to take away from that? Yeah, parks are different. Okay, good. I mean, this could be part of another model you work on to include this in, for sure, right? I have a feeling of I wonder if some of this stuff will come back in like the last two chapters when we try to pull together some more combined analysis. It'd be kind of cool. Okay, so this I thought was interesting. The idea here is, well, you guys getting a lot of, do the home runs, does it matter? Is it the pitchers giving up home runs, or is it the batters are good and they're getting the home runs? Which is the dominant factor in that? Certainly both are important, but which one's more important? And one way to approach that is what he does here. I really like this, is using a random effects model. So we just do a logistic regression again, like we did before, and we have some baseline home run rate, and then we have a random pitcher effect and a random batter effect. Beta is the random hitter effect, and gamma is the random pitcher effect. And you just assume, if you know about mixed models, this is pretty straightforward. It's a simple idea that you assume each pitcher and each batter has some effect that's drawn from normal distribution. And the standard deviation of that distribution is what we're actually interested in. Like, if the hitters have a larger standard deviation, that means the hitter effects tend to be larger in general. And same thing, if the pitcher standard deviation is bigger, it means the pitcher effects tend to be larger in general. That's the hypothesis going into this, or not the hypothesis, but that's the idea of this analysis. So everybody's seen that kind of thing before? Is familiar with that, I assume? Trevor's like, no. But yeah, but it's a powerful idea, and it can be used in all kinds of analysis. But here it's kind of a nice idea. Like, hey, let's try to see which one has the most important effect. So each individual hitter and pitcher in the database will get a number associated with it, which is his effect. But we don't really care about the number. We really care about the spread of the numbers. And so one way to do that is to use LME. I call it Lemur4, but LME4 is one library. You can also use other libraries. I tend to use BRMS, which is the Stan's Bayesian toolkit for doing that, because it has much more flexibility. You can do all kinds of correlation stuff and multinomial models, and it's just a very powerful toolkit. But for this one, this is certainly good enough to use this function. And to represent those kind of mixed terms, you use this syntax. This is called a grouping term. And this just says that for each pitcher, we should have an intercept. That's the one. You can also do slopes for more complicated models and interactions and all kinds of things with groups. If you're not familiar with that, certainly recommend something like Regression and Other Stories. Fantastic book, uses BRMS, I think. But anyway, it doesn't matter what it uses. It's a great book. Covers this. Actually, it covers it kind of toward the end, but it's a good book anyway. Let's see. Anyway, the point is you do this fit, and what we really care about is the sigma p and sigma b, which we can get from using this function varchar on the fit, and we find out that the pitcher effects are quite a bit smaller than the batter effects. That's probably you would have expected. That in other words, there's a lot more variation in home runs due to the batter than due to the pitcher, which suggests that the batter is at least more important in the duel, as it were, in terms of what the outcomes were. Okay, so this last section, he does this thing. He says, well, look, in 2021, 2023, the home run hitting seemed about the same, 1.2 home runs per game. So there wasn't a lot of difference from a global perspective or from a complete summary perspective. But he says there might be some differences when you're considering launch properties, right? So what he wants to do is say, let's look at the differences when we bin the space into different bins for different launch angle and launch speed. And then we'll look at changes across those two seasons in home runs, balls in play, or more importantly, the rates of both of those. In particular, he's interested in the balls in play rate in each bin. So that's the number of balls in play in that bin. All the data we have is all balls in play, right? But it's balls in plays in that bin divided by the total number of balls in play. So it's meant to show where the balls in plays are concentrated on. Although now I don't think I actually put that plot in here, but it's in the book. And then the more important one perhaps is the home run rate, which is for the balls in play in that bin, what fraction of them were home runs, right? So it's conditional on that. And so I'm not going to go through the details. These functions are in the book, but I just put them in here for completeness, and also so that the code would work. But he just defines a function to just calculate those bin rates. So he just uses the cut function to, you give it the breaks, and you give me some breaks. Give it the breaks and give it the StatCast balls in play data, and it will compute. This function will do the cuts, and then it will compute the total balls in play, the home runs, and then the rates. right? So it's just those same formulas expressed in code. And then this I definitely don't want to go into too much, but this just is a function, so you could make nice little plots of those. So here's an example of just for just 2023 home runs per bin. Now this is just total home runs per bin, and this is just to show kind of what it looks like. But you can see, yeah, sure, as we saw before, most home runs happen at higher launch speed and for medium angles. So that does make sense. So this is not a proportion, but just all the home runs. But you can do your own proportion by eye, as it were, for totals. But we really care about is the rate per bin. So if we took 861 here and divided it by, well, I don't have here, but if I divide it by the total balls in play, then you would get the home run probability for that going in that direction. But we really want to know is, hey, given the ball was already hit in that direction, that is, the ball's already, he calls it carry, right? The ball's going in that direction. It's going to go in that launch angle and launch speed. How many of those, what fraction of those turn into home runs? That's the home run rate by bin. So that's a complicated description, but since we already calculated, it's simple to plot. All we got to do is call the same bin plot thing and just say, hey, we want home run rate because we calculated it already. And here we can see that for 2023 in any event, if you did hit it it's kind of the same story still, but if you hit it with high launch speeds, yeah, if you're hitting that direction, that's you're more likely to get a home run, given that you hit it in that direction, conditional on that. And the only reason we care about that, though, is because we want to compare that, that carry from year to year. So to do that, he suggests, well, if you're near the borderlines of 83, 93, you'll Ricardo has a plot of the heat map version. Oh, nice. That's cool.
Yeah, it's easier to distinguish the colors than the numbers.
That's true. I should. That's good. That's a good
Most
idea.
of the time, yeah.
Yeah, that's a good idea. I didn't think of that. So he does a comparison between the seasons, and the idea is that, well, we worry about edge effects, so we'll convert this to, like usually when you do probabilities, we'll convert it to on the logic scale, and that's all this does here. And he's going to take then the difference of the logics and compare those from 2023 to 2021, and that's what this next plot is. Well, first this is the difference in balls in play logics, and I don't really see that these are big differences, but he claims that, hey, there's a lot more in 2023 balls that were hit hard in play. But I don't know. These look like small numbers to me. So I said, are these significant differences? Well, we need to really have errors on these to really know. We should really do a slightly different analysis where we calculate errors, maybe do some kind of regression. Might be better. I don't know. So then now we're back to the other question, the changes in carry. Given launch variable, how is the probability of ball in play? How is the probability that a ball in play becomes an 8 home run? How does that change? So similar calculation, now we just look at the home runs, convert them to logits, and take the differences as well. And we can plot that. Here we do see some differences that could be significant. Again, you really should have error bars for everything you do, but that's okay. This is fine. And the biggest change, obviously, is here at this very high launch speed and 30 to 35 launch angle, where there is a decrease in getting successful home runs in that direction. And there's also a decrease in this for getting successful home runs in that direction too. I don't know. He says that's offset by how many balls were hit, but it looks like to me, less balls too are about the same. So I'm not sure. I didn't follow that logic. I don't know if anyone else followed that, but I couldn't follow that logic on that. The only other thing I did is I said, what does this actually mean that it was down by, what was down by minus 0.1661, the difference in logits? So I just did a little, let's think about this a little bit. What does this mean? The difference in logits from 2023 to 2021 is this. Well, we can use our well-known property of how logarithms work and combine these together and see what this really is the log of the odds ratio between those two. And so that turns into a log ratio of about 0.5 if you exponentiate it. So that means that the home runs odds went down by a factor of 2 from 2021 to 2023. And I didn't put it in here, but if you do the math, you look back at the probabilities were, that means that it was like about 93% in 1981, and now it's 84%. So that's what the real change is. So that's again, we need error bars to know whether things are significant or not, but they sound like a big change in any event. But I don't see. He does say he thinks this is compensated by more balls hit hard, because the rates per game were about the same. So I didn't quite follow the threads in that connection. I don't know if anyone else did or not. Anyone have any comments on that part of the chapter? Take that as a no. So that's basically the chapter. I didn't do the exercises. Is there anyone has any like input on that? If anyone did any of the exercises they want to share? I think we still have some time, probably lots of time. I talk fast, yeah. 30 minutes. 30 minutes to get through that. But if anyone has anything you want me to go back to, or any homework problems that they did, or anything else they want to show, speak up. Okay, hold on. Not everybody all at once. Just
Well, talking in
key.
general, I tried to read this book a few years ago when it was, I think, the first edition, and now with the second or third edition, whatever we're on. The authors obviously added more material, but some of this
Yeah.
material towards the end are not necessarily full chapters, just to be kind of aware where we're at.
Oh, yeah, I noticed that. Yeah.
Next week, I of course wanted to cover Quarto, some of the new stuff, at least Quarto as opposed to R Markdown. I've been using it a lot, but if anybody has any general questions about Quarto, please put them in the Slack and I'll try to address them next week.
Oh, okay. Cool. Appreciate that. I think that's all I had on this. I mean, I think it was an interesting chapter. It's kind of fun to play with the data and see what you could do with it. I wish I had more time. I would love to go back and do like a proper, BRMS regression on this question of changes between seasons of the home run effects, but I didn't have a chance to do that. I did start messing around with it, but I didn't get too far on it. So real work took precedence over it, but it's something I leave that as exercise to the reader. You could continue. There's a lot of like open-ended things you could do with this data. It's kind of interesting. It's just kind of like scratching the surface. So it really just kind of, I like this approach. Kind of just gives you some idea of what kind of things there are to do. So yeah, and I agree with you, Trevor. And yeah, those reports looked interesting too.
Ron, I posted a presentation that I found by Jim Albert, the co-authors, on home run hitting, and he goes, deeper into that discussion. Okay,
Cool.
I mean, it's a presentation, so I had to go slide by slide and see more or less, what is the progression. But it gives a little more insights on how to deal with the home run hitting.
Yeah, as we suspect that there's a lot more.
Oh
There's
yeah,
a lot in that StatCast data. I think the point of this book was kind of just give you like some flavor of the kinds of things you can do with the data. And that goal is well accomplished, I think. Yeah.
But by the way, Kershaw. We know Kershaw, right? Pitcher.
Yeah.
He reached the 3,000.
Oh, really?
Yep.
Oh.
Not this game. I saw him yesterday, but it was the previous one.
Okay.
In Los Angeles.
Nice.
So yeah, one more for the club. It's interesting that they were comparing Kershaw around 7 to 8 years. Okay, what was his statistics and how he's pitching now, and definitely there has been a decrease in the speed of the ball, but usually what the pitcher does is that he tries to be a little more wise in terms of what he can do in that region of the of the speed of the ball. Because for example, they were comparing to the to the challenger pitcher, and he is a 20-year-old guy, and he's going to be speeding a cheese or fastballs, etc. But you see Kershaw kind of tricking the batter in terms of, guess what I'm going to pitch now? You didn't get it. Okay. So it's not only speed, it's more, that psychology that the pitcher can develop over time. When he doesn't have the speed, at his as his main advantage. So that was interesting, to watch.
I didn't see that game. I haven't had a chance to watch a lot of games. I did watch the game where Shohei pitched his birthday. That was good.
Let me tell you, he's still doing his strikeouts.
You
I
guys, you
think
got,
he got
yeah, you
about
got,
5 or 6. So he's still adding, to
Yeah.
the, to the bucket.
yeah,
Okay. And he's pitching about, in average speed, it's about
Yeah.
87, 88.
Yeah.
It's not that
No, it's good.
speed
He's
anymore.
really good.
But,
Obviously, but
he gets more, a little bit more out of it. And, he starts, using his other tools.
yeah,
Okay. More creative on the change-ups and, the sliders and everything. Interesting to watch.
very interesting. Yeah. Okay, I'm gonna put the end button so that
Sure.